Hello everybody. Today we're going to discuss our dry ice puck on a ramp pivot exercise, and we're going to review a little bit of the graphs and the meaning that we've found in these graphs over the last few days. And then we're going to add in a new modeling technique. Well, not really a new one. We're just going to expand our motion mapping idea to talk about uniformly accelerated motion. So, in the dry ice puck on a ramp pivot, we got a position time graph that was a nice top opening parabola. And of course, one of the things we spent quite a bit of time discussing was the slope, and in particular, slopes of tangent lines. And if we check out and just draw a couple of tangent lines onto this position time graph, right, so that we can discuss the slope, right? Here's a tangent line early on, a little later, right? Tangent line here. What do we notice about those slopes? Are they constant? Are they increasing, or are they decreasing in steepness? Well, they are increasing in steepness. Are they positive or negative slopes? They are positive slopes. And given that this is a position time graph, what do those slopes tell us about the motion of the dry ice puck? Well, the slope of a position time graph is still the velocity. So by looking at these slopes, we can tell that we have an increasing positive velocity. When we drew the velocity time graph, right, that increasing positive velocity manifested itself thusly. We can tell it's increasing because zero velocity is right on the time axis. And notice, this is getting further away from the time axis, so bigger velocities. Right? It's positive because it's above the time axis, positive velocities. Right? And it's a velocity graph because I said it was a velocity graph here with the V, right? So let's look at this slope. Is the slope of this graph increasing, decreasing, or constant? Well, it's a straight line, so the slope is constant. Positive or negative? It's positive. And what does the slope of a velocity time graph represent? The new quantity that we've been discussing so far in this unit. And that is the acceleration. So we can tell we have a constant positive acceleration by looking at the slope of the velocity time graph. Well, no reason to just stop at position time and velocity time graphs. We could also make graphs of acceleration versus time. Now we know that in this case, the acceleration is constant, or uniform, if you will, and positive. So what would a uniform positive acceleration look like on a graph of acceleration versus time? Well, hopefully you're saying, well, constants are horizontal lines, right? And positive means it's got to be above the time axis. You with me there? So this is a constant positive acceleration. If it was a negative acceleration, it would be down here. Right? And in this unit, we're only going to look at uniform accelerations. So these kinds of shapes are going to be indicative of what we're going to see in this unit. We're going to see parabolic position time graphs. We're going to see diagonal linear velocity time graphs. And we're going to see horizontal acceleration time graphs. All are hallmarks of uniformly accelerated motion. All right. So let's create a motion map of the dry ice puck on the ramp. Now, the motion map, first thing you'll notice right away is we have taken our position reference line, and instead of leaving it as horizontal, we rotated the axis. Why? Well, for the same reason that we do it when we're drawing force diagrams, which is to make the motion one-dimensional. So we can talk about this dry ice puck going down the ramp instead of the dry ice puck going horizontally and vertically at the same time. And it makes the motion description easier, makes the math a heck of a lot easier, right, if we rotate our axes so that it's parallel to the incline, right? So I took my position reference line here and I just rotated it. And so now I'm going to draw position dots, right, at equal intervals of time. So, dry ice puck started at the top of the ramp, so it's up here somewhere. 1 unit of time later, whatever that was, a second. In our lab, it was a tenth of a second, right? The dry ice puck had moved down the ramp. Another tenth of a second later, it had moved even further down the ramp. But how far down the ramp compared to here? Should the next dot be equidistant? Hopefully you're saying no, it should be further. right? This should be a bigger separation than here. And the next dot should be even further. And the next dot even further. And the next dot even further. Why? Why should these distances be getting bigger? Well, because the object is accelerating, right? It's speeding up in this case. So if this is the same amount of time between dots, right? If it's going faster, it's going to cover more distance in the same amount of time. Right? So the dots should get further and further and further apart. Now I'm going to draw arrows to represent the velocity of the disk. Right? And those arrows are going to point in the direction that it's moving, which is down the hill, one-dimensional, right? Because we rotated our axes. But let's talk about this first dot. What was the initial velocity of our dry ice puck? Well, it was tied up to the top of the ramp, and then it was cut, right? The wire was cut, and then it was allowed to move. So it started at rest. So if this is my 0 time dot, the initial velocity is 0. So there won't be a dot at that highest point. Right? This is only if it starts from rest. Okay? It's starting from rest, so this is 0 time dot, no velocity here. 1 unit of time later, now it's moving. 1 unit of time later, now it's moving, but we said it's accelerating. It'll be moving faster, so what should be true about the length of the velocity arrow? It should be longer. And then it should be longer, and longer, and longer. With me? So watch that again, right? Right, so each one, the velocity arrow gets longer. So we can already tell by looking at the dots and by looking at the velocity arrows that this dry ice puck was speeding up. Right? We can tell in the dots because they're getting further and further apart. We can tell with the velocity arrows because they're getting longer and longer and longer. But for the first time, we had a new quantity, which we can represent graphically, as we just did, but we can also represent on our motion map. And that is acceleration arrows. Now I'm going to draw these in green, okay? And again, I'm going to draw one for each dot. There's different ways of doing this depending on where who's doing this. I like to put my acceleration arrows under my dots. See how I left kind of a big space underneath here so I can draw something? I don't want to attach it to the dot like this one because then they'll overlap and it'll be really hard to see, especially if they're not nice and color-coded like mine are, right? So you're going to want to, put them just underneath the arrow, or the dot, sorry. Now, should there be an acceleration dot on the acceleration arrow for the first dot? Well, we said on the first dot, that's 0 time, it's at 0 position, it has 0 velocity. But is it accelerating? Well, let's think about what would it look like if it wasn't moving and it wasn't accelerating. If something is neither moving nor accelerating, remember acceleration is the rate of change of velocity, how quickly your velocity is changing. So if you have 0 velocity and 0 acceleration, what would your object do? Nothing. Right? It would just sit there. No acceleration, no velocity. Right? It's not going to go anywhere. And this object is going somewhere. Right? So it does have an acceleration arrow under the first dot. Now you'll notice I didn't go under as in vertical. I went under at an angle, right? Because we have rotated our axes. And the acceleration will point down the hill. Right? As we saw in the lab, right? We got a positive acceleration. Now, this is uniformly accelerated motion as we found in the lab, in lab extension, and therefore, these acceleration arrows should all be the same length. Right, so there's one, right? There's one for that dot. Do you see how they're all kind of starting perpendicular, if you will, right? It's not straight down below, right? But everything is on an angle. So we can see here that we have a constant positive acceleration, right, pointing down the hill. We can see that our velocity is constantly increasing, right, as the object speeds up. So a new thing to put in. Now, I didn't teach you acceleration arrows prior to this because when we did the unit of constant velocity, there is no acceleration. So there was really no need for acceleration arrows. Right? Velocity is constant. We don't have an acceleration arrow because it's not changing its velocity. Right? Acceleration is how quickly you are changing your velocity. Right? How quickly you're speeding up or slowing down or changing direction. How quickly your velocity is changing. Right? So there's a couple of new things we can throw in for uniformly accelerated motion. Graphs of acceleration in time, which will always be horizontal lines if the acceleration is constant, and acceleration arrows, which go underneath the dots on a motion map, right, which show the acceleration, which represent the acceleration. The direction that it's pointing is the direction of the acceleration. The size of the arrow represents the size of the acceleration. Now, I'm not going to ask you to get as technical as mine are, but if you look, like if you take this arrow and add this arrow, you basically get that velocity arrow. And then if it gets that much bigger, you get that velocity arrow, and so on, right? But I'm not going to ask you to get a ruler out and make these perfect. It's just the general pattern is what we're looking for here when we're making motion maps of uniformly accelerated motion.